Hi students, welcome back to this tutorial. In this video, we can discuss about some basic points about number system. So, a number system means system for representing numbers. We have different such systems for representing numbers. But in this video, we can discuss about 4 such systems that are commonly using for representing numbers. Okay, so that commonly using such number systems are the decimal number system. We can also call it as the base 10 system. Another one, binary number system or base 2 system. Octal number system or base 8 system. And finally, this hexadecimal number system or base 16 system. So first, we can consider the properties of this decimal. Okay, we can discuss about this decimal number system here. So this decimal number system is also called as base 10 system. Why this 10? This is because here we can use 10 different digits for representing any numbers. What are the 10 digits? 0, 1, 2, 3 up to 9. Total 10 digits are used for representing different numbers in decimal number system. That is why this one is called as base 10 number system. Right? So, in the decimal number system, the position of the digit represents its value. In a number, the position of the digit represents its value. So consider one example. Here it is the number which is represented in decimal form. Right? The number is listed like this 1, 2, 3, 4, 5. The position of the digit represents its actual value. What that actually means? This means this 5 is actually present in unit position. So the value of this 5 is like this. 5 into the base 10. So 5 into 10 to the power 0 means 5 is present in unit position. So this is the value of the 5 in this particular number. Right? So next one is the 4. 4 is present in 10th place. Right? So the value of this 4 in this number is this one. 4 into 10 to the power 1. Right? Because this 10 is used here because this is of base 10 representation. Right? Next is this 3. 3 is present in place of 100th. Right? So, we can represent the value of this 3 as 3 into 100 or 3 into 10 to the power 2. 10 to the power 2 means 100. Next, this 2. This 2 is present in 1000 place of 1000. So, this 2, the value of this 2 is represented like this. 2 into 1000 or 2 into 10 to the power 3. And this 1 present in the place of 10,000. So, 1 into 10 to the power 4 or 1 into 10,000. So, the digit, the position of the digit indicate its value like this. So while adding all these values together, we get the exact value of this number in decimal form. Okay, so add up all these values. So this is the actual value of this particular number representation. What is it? 12,345. This is the value of this particular number representation. Okay, so keep this point in your mind. The position of the digit represents its value. This one is present in unit place, so its value is 5 only. This 4 is present here in its 10th place, so its value is 40. 4 into 10. This 3 is present in 100th place, so its value is 3 into 100, 300. This 2 is present in 1000 place, so its value is 2 into 1000, 2000. So on. So after find the positional values, after adding all these values, we get the exact value of this given number. Right? So consider one more example, but here the given number contains a fractional part also. This is the whole part and this is the fractional part. So in this case, how to calculate its exact value? For that, follow this method. This first consider or concentrate here in this whole part. Here this 5 is present in unit place, 4 is present in 10th place, 3 is present in 100th place. Right? So we can calculate its positional value like this. 5 into 10 to the power 0. 10 to the power 0 is 1 itself. So 5 into 1, 4 into 10, 3 into 100. So this is the value of whole part. Then after this decimal part, we need to calculate the value of this fractional part also. How to calculate? 6 is present just after the decimal point. Positional value is 6 by 10 or 0.6. 0.6 means 6 by 10. So here it is represented like this. 6 into 10 to the power minus 1. What is it? 6 by 10. That is 0.6. And 7 is present in the second place after this decimal point. That means 0.07. Right? The positional value of this 7 here is 0.07. How can we represent this 0.07? 7 into 10 to the power minus 2 or 7 by 100. This 8 present in which position? Third position after decimal point. That means 0.008. So, we can represent the positional value of 8 here as 8 by 1000 or 8 into 10 to the power minus 3. Okay, now calculate the positional value of each and every digit here. Now we can sum up the values. Right? Then get the exact value of this number. What is this? 345.678. Okay, so this is the method for getting the exact value of a number in any of the given system. Okay, so we have already discussed the properties of decimal number system, right? This decimal number system, that is we are using in our day-to-day life. Okay, so now we can consider the next form of number system, that is this binary number system. Okay, so binary number system means base 2 system. Why this 2 here? This is because here we use 2 digits. What are they? 0 and 1 only. So, in this case of binary number system, each of the digits present in the number is called it as bits. Okay, each of these digits present in the number is called as bits. So consider one example. The number is this 10101 and the base is 2. The number is represented here in binary form. The number is 10101. Actually, we can follow this particular syntax for representing binary number, or we can simply write like this. No need to specify the space. Okay, now we can identify which decimal number is represented by this binary number. Okay, or calculate the decimal equivalent of this particular number, or we need to evaluate its exact value in decimal form. How to calculate? We can follow the same method that we have already discussed in our previous decimal system. Okay, so we need to calculate the positional value, but the difference is here the base is 2. So this 1 is represented, its value is represented like this. 1 into 2 to the power 0. The positional value of this 0 is represented like this. 0 into 2 to the power 1. And this 1 represented like this. 1 into 2 to the power 2. This 0 is represented like 0 into 2 to the power 3. And this one represented like this 1 into 2 to the power 4. So each of these terms represent its positional value, right? So after identifying the positional value, we can simply sum up these values. So the decimal equivalent of this particular binary number is 21, or its exact value is 21. The conversion from this binary to decimal equivalent is considered here because we are usually following the decimal system in our day-to-day life. Okay, so we are actually familiar with this decimal number system. So the decimal 21 is equivalent to this particular binary number. So this is the method of evaluating the decimal equivalent of a given binary number. Right, consider one more example, but here it is a number containing a fractional part. Whole part is this 101 and decimal part is 110. This is again in binary system. So we can calculate or evaluate its decimal equivalent. How it possible? Follow the same method. So start from this point. This one is present in the first place. So 1 into 2 to the power 0. This 0 is present next position. So 0 into 2 to the power 1. Then this 1, its positional value is 1 into 2 to the power 2. So this 2 used here because 2 is the base of our binary system. Then consider the fractional part. 1 into 2 to the power minus 1. And this one, the positional value of this one is 1 into 2 to the power minus 2. And the positional value of this 0 is 0 into 2 to the power minus 3. Right? So all these are the positional values of each and every bits present in this number. So after finding all these positional values, we can sum up these values. Right? This 1 into 2 to the power minus 1. 1 into 2 to the power minus 1 means 1 by 2. That is 0.5. And 1 into 2 to the power minus 2 means 1 by 2 square or 1 by 4. That is 0.25. Here it is 0 into. So this term is, its value is 0 itself. Right? So after performing the addition, here it is 4 plus 0 plus 1 plus 0.5 plus 0.25 plus 0 is 5.75. So the decimal equivalent of this particular binary number 101.110 is 5.75. Right? So this binary system basically used in computer and other digital devices in order to store our data. Right? So binary system is used for storing data in digital devices. And digital devices, data are stored using digits 0 and 1. Or a sequence of zeros and ones are used for representing data in digital devices. Okay, now we can consider our next system, that is octal number system. Here, the system is of base 8. So we can call it as base 8 number system. So what are the 8 digits used here in this octal number system? These are that 8 numbers 0 to 7. Okay, using this digit, we can represent numbers. So this is one example for an octal number 2301. This number here, these numbers are used from this 8 digit. So this is an example for our octal number. Okay, so now we want to calculate the decimal equivalent of this octal number. How to calculate the decimal equivalent of this number? For that, we need to find the positional value. This 1 is present first. So 1 into a to the power 0. This 0 as the next value. Okay, so the 0, its positional value is, the positional value of the 0 is 0 into a to the power 1. And this 3, its positional value is 3 into a to the power 2. And this 2 is present next, its positional value is 2 into a to the power 3. Okay, so these terms represent the positional values of different digits present in this number, right? So after performing the summation of these values, we get a number 1224. So this is the decimal equivalent of this particular number, which is represented in octal number or in octal system. Okay, consider one more example. So here it is a number, octal number, which is having a fractional part. Now find out the decimal equivalent of this number. How to calculate? Start from here. 3 into a to the power 0 indicate the positional value of 3 here. And this 2, the positional value is 2 into a to the power 1. And the positional value of this one is 1 into 8 square. Plus, now consider the fractional part. The 6 is present just after this decimal point. So its positional value is 6 into 8 to the power minus 1 or 6 by 8. And 7, its positional value is 7 into 8 to the power minus 2 or 7 by 8 square. Right? So these are the value 64 plus 16 plus 3 plus this is 0.75 and this is 0.109. So after adding, we get a value 83.859. This is the decimal equivalent of this particular number represented in octal system. Right? So this particular octal system is used in some of the computer system like UNIVAC, AC1050, PDB-8, etc. This one is not that much common. Okay, now we can consider our next system, that is the hexadecimal number system. So here hexa means 6 and decimal means 10. So total 6 plus 10, 16 digits are used here. So this one is a base 16 system. So what are the 16 digits using here? The digit from 0 to 9 and 6 alphabet. What are the 6 alphabet? A, B, C, D, E and F. Okay, so these 16 digits are the base of our hexadecimal number system. Using this digit, we can represent any number in this hexadecimal system. So, this A, the symbol A actually indicate our decimal 10 and B indicate decimal 11, C, symbol C indicate decimal 12 and D is equivalent to decimal 13 and E is equivalent to decimal 14 and F is equivalent to decimal 50. Okay, so keep this in your mind. The alphabet A in our hexadecimal number system indicate or equivalent to decimal 10 and B equivalent to 11 and so on. Right, so consider one example, a number represented here in base 16. 1, 2, 3, 4, 16. Base 16. And one more example, 19FDE. This is also valid because we can use 6 different alphabets for representing a number in hexadecimal form. So EDF all present in that digit sequence. So this is again a valid number in hexadecimal system. Okay, so next task is to find out. Next task is to evaluate the decimal equivalent of this particular number. Okay, how to calculate? Here this is a base 16 system. So our task is start from here. E into 16 raised to 0, D into 16 raised to 1, F into 16 raised to 2, next is 9. So 9 into 16 raised to 3 and 1 into 16 raised to 4. So these terms indicate the positional values of each of these digits. Right? And one more here, this E. From this list, E is equivalent to decimal 14, F is equivalent to decimal 15, D is equivalent to decimal 13 and so on. So using that, we can replace this E with 14, D with 13, F with 15. Now evaluate its positional value like this. Then we can add and get a number like this. Decimal number is equivalent to 1,06,462 in decimal. Right? So this is the method of converting an hexadecimal number to its decimal equivalent. Consider one more example. Here it contains the fractional part. Our task is to find its decimal equivalent. Okay, follow the same method. So first consider the whole part. 0 into 16 raised to 0, 1 into 16 raised to 1. Then the fractional part 0 into 16 raised to minus 1, a into 16 raised to minus 2. A means or a is equivalent to decimal 10. Right? So the value is 16.039. So this one is the decimal equivalent of this particular hexadecimal number. Okay. So this hexadecimal system is commonly using for representing or simplifying the binary number system, mainly used in order to describe the location in computer memory. Okay, using for describing the memory address locations. Usually the locations are specified in binary and we can convert into a user-friendly form, that is into an hexadecimal form. So usually the memory locations are addressed using numbers which are present in hexadecimal form. Okay, so all these are four different commonly using number system. So here you have certain questions. Try to solve these, and if you have any doubt, please put that doubt in the comment section. I will help you to solve personally. And also try to find out the answer and put your answer to the comment section. Okay guys, so we can discuss about conversion from one system to another in our next video, and also we can discuss or we can learn some simple method to convert from one system to another in our next video. Okay, thank you. See you soon.